To keep a small electric aircraft in the air as long as physically possible, every gram of weight and aerodynamic drag must be perfectly accounted for. The core engineering challenge requires taking a completely blank sheet of paper and mathematically defining the exact dimensions, weight, and power of a vehicle to guarantee it can complete a specific mission. We call this defining the design point. This creates a circular dependency. Wing geometry dictates drag, which determines the required power and the resulting battery mass. But that battery mass then dictates how much lift the wing must produce, which changes the wing geometry. At this level of design, engineers cannot rely on intuition or basic flight analogies. They use a conceptual sizing loop to solve these interdependent variables. This sequence requires 3 strict calculations: predicting aerodynamic drag, forcing mass variables to converge, and defining the operational limits through energy-based constraint analysis. By executing this iterative cycle, we mathematically prove that an aircraft will survive the physical demands of its mission long before we cut a single piece of carbon fiber. The sizing process begins by establishing the aerodynamic penalty of our airframe through a drag polar. As an aircraft moves, it generates total drag. This is the sum of 2 distinct components: the parasitic profile drag created by the shape of the vehicle, and the induced drag created as a direct byproduct of generating lift. This chart plots the lift coefficient against the drag coefficient to map our required thrust. If our goal was to fly as far as possible for maximum range, we would aim for this specific minimum drag point, known as L/D max. Our objective here is maximum endurance, meaning we only care about total time aloft. To maximize time, minimizing drag is the wrong approach. We must minimize power. Because velocity acts as a cubed multiplier in the power equation, the lowest required power occurs at a slower speed than the lowest drag. This specific mathematical optimum sits at the peak of the CL⁵/CD curve. Flying at this absolute minimum power setting introduces a critical mechanical danger. It forces the aircraft to operate precariously close to its stall speed, leaving almost zero margin for physical control. That danger compounds when we factor in the actual flight path. A loiter mission requires flying in continuous patterns. Banking the aircraft into a turn forces an increase in the aerodynamic load factor on the wings. Because stall speed scales directly with the square root of that load factor, any turn artificially raises the minimum speed required to keep the aircraft from falling out of the sky. To ensure the airframe remains controllable under these stresses, we must deliberately step away from the absolute aerodynamic optimum, injecting a strict 20% margin above the turning stall speed. With our required aerodynamic power established, those theoretical forces must be translated into physical mass. Unlike a jet or piston engine, an electric propulsion system introduces a distinct thermodynamic reality. There is no fuel to burn off. The gross takeoff weight remains completely static from launch to landing. The total gross weight is composed of 3 fixed variables: the empty weight of the airframe, the weight of the battery, and the weight of the payload. Estimating the airframe weight using standard statistical data from manned fuel-burning aircraft artificially inflates the mass estimations for a small electric vehicle. Applying these standard equations mathematically kills a viable design. To solve this, we apply regression models derived exclusively from modern, lightweight composite drones to ensure our empty weight fraction reflects the reality of sub-300 kilogram vehicles. Because empty mass and battery mass are defined as fractions of the gross takeoff weight, the equation cannot be solved in a single pass, while the total weight is still an unknown variable. We resolve this through an iterative mass convergence loop. We feed an initial guess for the gross weight into our fraction multipliers, which calculates a resulting available payload weight. The loop then continually adjusts the gross weight guess up and down. The iteration stops when the calculated output precisely matches our required mission payload. This exact convergence calculation forces our abstract aerodynamic power requirements into hard mass numbers, providing the firm constraints needed to finalize the vehicle geometry. To synthesize all of this aerodynamic and mass data into a final geometry, we deploy energy-based constraint analysis. This constraint graph evaluates the aircraft's performance limits by mapping wing loading on the x-axis against specific power on the y-axis. We map specific power instead of the traditional thrust-to-weight ratio because propellers deliver relatively constant power across their speed range, unlike jet engines, which deliver constant thrust. The foundation of this graph relies on specific excess power. This equation equates the aircraft's physical ability to climb or accelerate directly to the net propulsive power installed in the airframe. We outline the physical boundaries of our mission by plotting the required power for takeoff and the required power to maintain a constant speed climb. The approach and landing phase introduces a separate mechanical constraint. Safely bringing the aircraft back to the ground is a pure aerodynamic lift problem that functions entirely independent of the motor's power. Because we require a slow, safe landing speed, the physics of our wings impose a strict limit. We hit a fixed maximum allowable wing loading, regardless of how much power we install. The blank region trapped between these intersecting mathematical walls forms our feasible design space. If our aircraft's parameters fall inside this zone, it has the physics required to survive the flight. Our final task is extracting the exact coordinates for our design point from this feasible space. Standard engineering logic points toward choosing the highest reasonable wing loading and the lowest specific power. This ensures you carry the smallest engine and the smallest wings possible. Small electric endurance UAVs demand an exception to this rule. Because a battery never loses mass like a burning fuel tank, the vehicle flies slowly and heavy for its entire lifespan. As a result, induced drag dominates the flight profile. Induced drag is inversely proportional to the square of the wingspan. Shrinking the wings to save structural weight creates a massive penalty in the power required to fight that induced drag. To counter this, engineers deliberately oversize the wing. Selecting a low wing loading drastically cuts induced drag, accepting the minor penalty of added skin friction. Extracting these exact coordinates yields actionable specifications, the required square footage of wing area, and the precise motor shaft power. Through strict cycles of aerodynamic prediction, mass convergence, and energy constraint analysis, we have forced a completely abstract mission concept into physical hardware blueprints.